This is part 3 of the module on economic and hydrologic modeling. In the previous part of this module, part 2, we built a model of a farmer's production decision. In this part of the module, we are going to use that model in order to learn something about a farmer's behavior. So remember from the previous part that we simplified a farmer's production decision in the real world by making some assumptions. And in particular, we made some assumptions about the factors that go into a farmer's production decision. We took those factors and gave them variable names. And then we used the fact that profits equal revenue minus costs in order to come up with the farmer's profit equation. Now, we have this profit equation, and the question is, how is this equation going to be useful to us as a model? So let's try to answer one interesting question about a farmer's production decision. Notice when you look at the farmer's profit equation that water as an input appears twice. Water appears here because if the farmer applies more water, he will get a higher yield for his crop and therefore obtain a higher revenue. However, because it is costly for the farmer to pump groundwater, every unit of water that is applied to the crop is also going to add costs to the farmer. So here's an interesting situation where if the farmer uses more water, it increases his revenue, thereby increasing his profits, but more water use will also increase the farmer's costs, which will decrease his profits. So what is the right amount of water use for the farmer? There's probably some sort of sweet spot at which there's a water use level that will maximize the farmer's profit. Okay? And this is going to be known as the profit maximizing level of water use. And the question here is, can we use this model in order to figure out what that profit maximizing level of water use is? And it turns out that we can. We can use this model and some calculus methods to find out. For now, suppose that the farmer cannot change the area of land planted with the crop. So in reality, the farmer can also choose the level of L, the number of acres of the crop to plant. But right now we're trying to focus on how the farmer makes a decision about how much water to use. So for now, let's ignore L. Let's just assume that it stays fixed and focus on our variable W, which is water use. So again, this is the profit equation that we derived in the last part, and that was also on the last slide. We're going to take the derivative of the profit equation with respect to W, the volume of water applied to the crop. Okay, and what is that going to give us? It is going to give us d pi dW. What this means is it gives us the change in profits due to a change in water use. Okay, and so if you recall from your calculus class, if you want to take a derivative of this expression with respect to W, then you got to see where all the W's are. First of all, you see it here in the yield function, and so you got to take the derivative of that. So the derivative of the yield function is going to be dy dW, but the yield function is also multiplied by p, so you'll have to carry the p over here in the derivative. The W also appears here on the cost side, but it is only a linear term. That is to say, it is to the first power. And so recall again from your calculus class that when you take the derivative of a linear expression with respect to the variable, then you just drop the variable and you keep the coefficient. In this case, the coefficient is a CW. Both the yield function and the cost expression are multiplied by the L, okay, the number of acres planted, and that carries over, again, due to the laws of calculus. So d pi dw is going to be L times the quantity P times dy dw minus CW. Now that we have the derivative of the profit function with respect to water use, we want to find out what level of water use is going to yield the highest profit. And you should have learned in your calculus class that the way to do this is to set the variable, the derivative equal to 0. By setting the derivative equal to 0, you will find the stationary point. And that is the point at which the value of the expression that you took a derivative of is the highest. So this is the derivative expression that we derived in the last slide, and here we set it equal to 0 in order to find the maximum. Now the L is just multiplied to the whole expression here, so if we divide both sides by L, we just get the inside of the brackets equal to 0. And then if we add C sub W to both sides, then we get this condition. Because we set the derivative to 0 and came up with this condition, we know that this condition must be fulfilled in order to maximize profits on the farm. Now, this looks like a whole bunch of variables, but what this tells us in an economic sense is that in order to maximize profits, the farmer should use enough water. He should choose W so that the marginal revenue product of water is equal to the marginal cost of water. This side of the equation represents the marginal revenue product of water, and this side of the equation represents the marginal cost of water. So, to repeat this in another way, in order to maximize profits, the farmer should use enough water so that the marginal revenue product of water equals the marginal cost of water. Let's define these two terms, the marginal revenue product of water and the marginal cost of water. The marginal revenue product is the change in revenue that results from the addition of one extra unit of an input, in this case, a unit of water. And marginal cost, term marginal cost, is the change in cost that results from the addition of one extra unit of an input. Okay, so in this context where we're dealing with water, the marginal revenue product water is the additional revenue that the farmer will get if he uses another unit of water. And the marginal cost of water is going to be the additional cost that the farmer will incur in order to use another unit of water. And in our analysis here, we determine that the marginal revenue product of water must equal the marginal cost of water. And so why is that? The model tells us that that must be true for the farmer to maximize profits. But we want to think about why that is the case. So suppose that the farmer starts out using no water, and then the farmer increases water use 1 unit at a time. Okay? As long as the marginal revenue product of water exceeds the marginal cost of water, the farmer should continue to increase water use. Right? So if the additional revenue that the farmer is getting by using an additional unit of water is greater than the amount of money that he's paying to use that unit of water, then that additional unit of water is adding something to profits, right? So he should use that unit of water, and he should increase. He should keep on using more water. But eventually, the marginal revenue product of water will start to decrease. Okay? You can add more and more water to your crops, but at a certain point they're not going to increase in yield anymore. And so as soon as the marginal revenue product of water, as soon as you get to that point where an additional unit of water isn't going to increase your revenue very much, you want to stop using more water, right? Because additional units of water are going to cost you more money. Okay? So you don't want to be in this situation where the marginal revenue product of water is less than the marginal cost of water, because there the farmer is going to be paying more for that unit of water than what he will be getting in additional revenue from using that unit of water. So, to summarize this part of the module, we started out with the farmer's profit maximization model that we built in part 2 and applied some methods from calculus in order to learn about how farmers make decisions about their water use. And we learned an economic lesson from this model, which is that in order to maximize profits, a farmer should use enough water so that the marginal revenue product of water equals the marginal cost of obtaining that water. The exercise for this part of the module is the following. So recall the condition for profit maximization, which we obtained by setting the derivative of the farmer profit equation equal to 0. This was the last line that we came up with after taking the derivative of the farmer profit equation and setting it equal to 0. Note that fixed costs, C sub f, is nowhere to be found in this condition for profit maximization. C sub f was part of our farmer profit function, our farmer profit equation, but it's no longer here in the condition for profit maximization. So what this means is that when a farmer chooses a level of water in order to maximize his profits, he should not think about his fixed costs when he makes this decision. So the question that I want you to think about is, why should fixed costs not be part of the farmer's decision on how much water to use? Why are fixed costs not a relevant factor for the farmer to decide how much water he should use? Good luck answering this question.